Okay, so I hope this is not too overwhelming, but let me give you a little preface. So we've talked about functions and their derivative functions, and that's going to be a very important thing to be able to do. Given a function, find its derivative. Now we have a definition for the derivative function, but in practice, this is very difficult to work with, especially if you have a function that is very complicated. It consists of combinations of many different relatively simple functions. And so what we want to develop now, just like we had the limit laws that allowed us to quickly evaluate limits without actually using the definition of the limit, we want to develop some differentiation rules. So that's exactly what we have stated here. These are differentiation rules. And if you look down this list, most of them are just showing how if I combine a function in a certain way, what happens to the derivative of that combination of functions. The first one, actually the first two, are kind of the most basic. So if we have a constant function, so a function whose graph is actually a horizontal line, it's not surprising that the derivative is 0, because the slope of a horizontal line is 0. For the second one, the identity function, this is just the function whose graph is the line y equals x that has slope 1. So it's not surprising that the derivative for each x value is 1. Now we can get a lot of real estate out of these two basic functions by looking at how functions can be combined. So we can multiply a function by a constant. So we see that if we multiply a function by the constant and take the derivative, we just multiply the derivative by the constant. If we add two functions together and take the derivative, we just sum the derivative of the two functions. So everything seems to work out the way we would expect. The first thing that gets a little interesting is actually the product rule. Now the product rule says that if I multiply two functions together, this is what I need to do. I need to take the derivative of one times the other plus the one times the derivative of the other. So it's not just as simple as multiplying the derivatives. There's actually something a little bit subtle about taking the derivative of a product of two functions. And then if you look at the quotient of two functions, so if I divide two functions and take the derivative of that quotient, now we're starting to see a really complicated formula. And definitely the quotient rule is the most intricate. It's also a little bit tricky because you're subtracting. It's related to the product rule, but because you're subtracting, you actually have to remember which function to take the derivative of first. And so there are some mnemonics to remember this that I'll kind of go through when we do an example. So you take the bottom times the derivative of the top minus the top times the derivative of the bottom. So I like to think low d high minus high d low. Low is the bottom function, d high is the derivative of the top, minus top, so high, times derivative of the bottom. And that's going to be important just to do several examples to just memorize that. And then you divide by the bottom function squared. The power rule is really nice. This one's really quick to remember, and it's really easy to apply. So if we just have a power function, function x to the n, then its derivative is just n, so you bring down the power, and then you take x to 1 less than the original power. Okay? And we will actually go through and justify all of these differentiation rules from the definition of the derivative. The only one we're not going to do right now, and I just wanted to make a note, is that the derivative of this exponential function e to the x is itself, which is really cool. So what that means is if I want to find the slope of a point on the graph of e to the x, then it's the same as just the evaluation of the function, which is really interesting. And we'll talk a little bit more about the exponential function later, but for now, let's actually go through and see why all of these are true. Now, I don't think it's important to memorize how to justify all of these. Now, the first few are going to be really easy. The product rule and quotient rule, even the sum rule, require a little bit of trickery to see why they're true. But I think it's worthwhile just to see it done one time and to say, okay, the product rule, it's coming from the definition of the derivative. Now I can just use it. And it's going to make finding derivatives and derivative functions a lot easier, as we'll see in the examples. Okay, so let's see why the derivative of a constant function is 0. And now this is really straightforward, and in fact, you could even just argue, like we did before, that a constant function is a horizontal line and has 0 slope, and that's perfectly valid. But let's see how it goes using the definition of the derivative. So f prime of x, just by definition, is the limit is h goes to 0 of f of x plus h minus f of x all over h. Okay? And here comes the hardest part of this little proof of the derivative of a constant function: evaluating the constant function. And so when we talked about the pre-calculus review, I told you that maybe one of the trickiest things about constant functions is just accepting that no matter what the input is for a constant function, the output is the same. So what is f of x plus h? It's just c. It doesn't matter what I plug in. I always output c. What is f of x? It's just c. All over h. But then this is just the limit is h goes to 0 of 0. Because c minus c is 0, h I'm actually assuming is not 0 because I'm taking the limit as h goes to 0. But then the limit of a constant is just that constant, so we get 0. And so that justifies why, using the definition of the limit, the derivative of a constant function is equal to 0. All right, so let's try to tackle the identity function. F of x is equal to x. Again, geometrically, we can think that the graph of this function is just the line y equals x, which has a slope of 1, so it should not be surprising that the derivative is 1 for all x. But let's see why that's true using the definition of the derivative. So if we take the limit as h goes to 0, so we're trying to find f prime of x, so the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, what's f of x plus h? So the identity function just gives the input as the output. So since the input is x plus h, the output is just x plus h. And then f of x is, of course, just x over h. But then look what happens. We have x minus x, so that's 0. So we're just taking the limit of h over h, which is just the limit of 1, right? Because I can cancel h, because I'm taking the limit as h goes to 0. So I'm assuming that h is not equal to 0. But then the limit of 1 is just So we see the derivative of the identity function is 1, justified by using the limit definition of the derivative. Okay, so here we're stepping up a little bit in abstraction because we're not dealing with a concrete function, an explicit function. We're just saying given any function that has a derivative, so a function for which that limit exists for each x, and then we have a number c, if we multiply f by c and then take the derivative, that should just be c times the derivative of f of x. So let's see why this is the case. So if I look at c f prime of x, this is going to be the limit as h goes to 0 of what? So the function I'm evaluating is cf. So this should be cf of x plus h minus cf of x all over h. And so it might be worth just reminding you kind of what this notation really means. So in parentheses here I have cf, so the function is cf. And what that means is that I take the function f, evaluated x plus h, and then multiply by c. Okay. So what I get here, limit as h goes to 0, this is just going to be c times f of x plus h minus, and then we're going to evaluate f at x and then multiply by c. So this is going to be c times f of x all over h. But I can factor out a c here. And using the limit laws, I can actually factor it all the way out, outside of the limit, because the limit of c is just c. So it's the limit as h goes to 0 of f of x plus h minus f of x all over h. But now I'm assuming that f is a differentiable function. So that means that this limit here, right there, exists and is actually equal to f prime of x. So then this is equal to c times this quantity, or this function, which is f prime of x. And it's a little bit subtle what we're doing here, but the good news is things are behaving exactly like we would expect. Okay, so if I multiply a constant by a function and take the derivative, that's the same thing as taking the derivative and then multiplying by the constant. And we're seeing that here. And so it's a little bit strange because I doubt that you deal a lot with kind of this function composition notation a lot. And that's really the only difficulty in this constant multiple rule. And in the other examples to follow, is just kind of the level of abstraction. You know, in reality, you're going to be given a function, you know, x squared or x plus 2 or square root of x, and you just want the derivative. You're just going to do it. But these abstract rules kind of just give you a framework or a justification of why you can just do the derivative the way you want to. Okay, so again, this is going to be a little bit abstract to justify, but it's a very useful fact that if I'm just adding two functions together, like if I add together power functions, then I'm going to get a polynomial. So this is kind of giving me a way to take the derivative of a polynomial. Then all I do is just take the derivative of each piece that I'm adding together. Okay, so let's see why that's true. So if I look at f plus g prime, and now I'm assuming that f and g are both differentiable, so this will actually make sense when I get f prime and g prime. So this is supposed to be the limit, by definition, is h goes to 0, of f plus g, that function, so the sum of the two functions evaluated at x plus h, and then minus this function f plus g evaluated at x, all divided by h. Okay, so recall that when you evaluate a sum function at a point, you just evaluate each function at that point and add them together. So this is really f of x plus h plus g of x plus h, okay, and then minus, well, let's put this in brackets because we're really going to be subtracting everything over here, f of x plus g of x, because that's what happens when I evaluate f plus g at x. It's just f of x plus g of x, but I'm subtracting both of those quantities. And then, of course, we're all divided by h. And now, so I'm trying to show that this is equal to f prime of x plus g prime of x. But really, all the pieces are in place. I really just need to reorganize this quotient here, and then just apply the limit laws into the two different pieces. So what I'm going to do is I'm going to say this is the limit as h goes to 0. I'm just going to kind of reassociate things. So I'm going to put f of x plus h, and then I have minus f of x. I'm going to put the minus f of x over here, and then that's of course divided by h. And then I have this g of x plus h, and I'm going to take this minus g of x and associate it there, and then that's divided by h. Okay. So notice that I split up the fraction, but everything's still okay, right? Because these fractions have a common denominator. I could just re-add them together and kind of move things back around, and you see that this really is the same thing. But now I can take the limit of this difference quotient right here, the limit of that, plus the limit of that, but the limit of this is f prime of x, and the limit of this as h goes to 0 is g prime of x. That's where I'm just using the limit laws. So this really is f prime of x plus g prime of x. So nothing crazy going on here, just a little bit of reorganization to see that yes, if I add two functions and then take the derivative, that's the same as taking the derivative of each function and adding those derivatives together. All right, here's where things start to get really interesting. So if you find yourself lost, just hold on. It's going to be okay. But here, to show that the derivative of a product is given by this kind of strange, you take the derivative of each function and then multiply by the other, add them together, we're going to have to use some real mathematical trickery. And we're also going to have to use something that we mentioned in the last lecture, and you probably just brushed right over, the fact that if a function is differentiable, it is continuous. Okay, so that's going to be important. But first of all, you know, with any problem like this, if you're trying to show something, you just start by writing down what you know. Okay, so I'm trying to show that the derivative of this product is this. So let's just write down, by definition, what is the derivative of this product of two functions. So it's the limit is h goes to 0 of f times g evaluated at x plus h minus this function f times g evaluated at x all over h. Okay, so just using how we know how to combine functions, let's just evaluate what this is saying. So f times g evaluated at x plus h is the same thing as f of x plus h times g of x plus h. And then f times g of x is the same thing as f of x times g of x. And then all over h. Okay, so now with the sum rule, all we had to do was just move things around. Now here, it is not so easy because all of the pieces are not here to give me this. So if I'm looking for something that looks like f prime of x, I'm looking for something like f of x plus h minus f of x. And then I also need something that looks like g of x plus h minus g of x. So this is where the trickery comes in. So I'm going to do something that we've kind of done before, and I'm just going to strategically add 0. Okay, so adding 0 to anything, well, doesn't change it. So what I'm going to do is I'm going to write that this is f of x plus h times g of x plus h, and then I'm going to subtract f of x times g of x plus h. Okay, so that's coming from nowhere. So I'm subtracting something. Well, then I better add it back to make sure that I'm not actually changing the value of this expression. And then finally, I have minus f of x times g of x. And then all of this over h. Okay, so step back, make sure you believe that this is actually true, that this is actually equal. And just to kind of help you, notice that this middle part is actually just 0. I'm adding and subtracting the same thing. Okay, so why did I do that? Well, now I'm going to factor. So notice that the first two terms here have a factor of g of x plus h. And the second two terms have a factor of f of x. So I can factor. Okay, so I'll take the limit as h goes to 0. Now I'll have g of x plus h. Okay, and if I factor that out, I'm left with what? F of x plus h minus f of x. That comes from just factoring out g of x plus h here, just looking at the numerator, and then plus, well, let me factor out f of x, and then what am I left with? G of x plus h minus g of x. And now I need to divide everything by h, but let me just divide each of these terms by h. Okay, and so because both of these terms have the same denominator, I can just write it as a single fraction like this, so these should be the same thing, but I'm just reorganizing it in a way that it's starting to look a lot like this, what we want it to be equal to. In fact, there's only one problem. Everything looks beautiful. So if I take the limit, I'm just going to apply the limit laws to take the limit of everything here. The limit of this guy is f prime of x. Okay, and then the limit of this guy is g prime of x. The limit of just f of x is just f of x. That's constant with respect to h. But then I also have this, which I'm going to leave for a second. So I also need to take the limit of g of x plus h. And so everything's great as long as the limit is h goes to 0 of g of x plus h equals g of x. So how do I know this is true? And what is this even saying? Think about it for a second. Let me just rewrite it for you. Let's let x plus h equal, say, y. Then as h goes to 0, y is approaching x. So this is the same thing as saying the limit is y approaches x of g of y is equal to g of x. But this is starting to look familiar. This is just saying that g is continuous at x. Now remember, we need this to be true. So if g is continuous, at x, we're done. So why is g continuous at x? Well, here's the key. G is differentiable at x. And we've shown that if a function is differentiable, wherever it's differentiable, it has to be continuous there. So because g is differentiable, g is continuous, and we can really conclude that this guy is g of x, which is exactly what we want. All right, so let's talk about the quotient rule. So the first thing to notice about the quotient rule is that it's not so different from the product rule if we define a new function. Okay, so what I can do is I can say f over g is really the same thing as f times the function 1 over g. So I can actually apply the product rule to this function f times 1 over g, but what I really need to know what to do is to take the derivative of 1 over g. Okay, so actually what we're going to do is we're just going to show that the derivative of 1 over g is given by a particular formula, and that it's compatible if we just apply the product rule to this situation. Okay, so let's see what the derivative of 1 over g is. So for 1 over g, the derivative by definition is given by this. Limit as h goes to 0 of 1 over g, that function, evaluated at x plus h, and then minus the function 1 over g evaluated at x, and then all over h. Okay, so let's just fill in what this actually means. Here, 1 over g evaluated at x plus h, that's kind of symbolic just to mean, okay, this is 1 over g of x plus h, and then minus 1 over g of x, all over h. And the trick here, so again, we have this complicated mess in the numerator. We want to get a common denominator and write this as a single fraction. So this is the limit as h goes to 0. And now I want to multiply this on the top and bottom by g of x, and this in the top and bottom by g of x plus h. So we're going to be left with g of x minus g of x plus h over g of x plus h times g of x, and then that all over h. But of course, this h is like over 1, and so we can do a little bit of manipulation here. And actually, we can just put h up in the denominator, like this. Okay, so dividing a fraction by a number, that number just goes into the denominator. That's a really useful trick to remember algebraically when you're simplifying things using algebra. So let's write this in a very suggestive form. So I'm going to factor out this 1 over g of x plus h and the 1 over g of x to have 1 over g of x plus h times g of x. And then times, I want to write this as, well, I'm going to factor out a minus 1, so I'm going to make this minus here, because I'm going to switch the order of these two. I'm going to write g of x plus h minus g of x all over h. Okay, and so take a minute, make sure you believe what I'm doing here. So if I multiply this negative 1 back in, notice I'll get back to g of x minus g of x plus h. So that's why I have to factor that negative 1 out. Everything else looks okay. And so what we have is the following. Note, just as before, g of x is continuous. And why do I know that? Well, it's right here, because g of x is differentiable. I'm assuming g is differentiable, and we have this nice result that differentiability is stronger than continuity. So if a function is differentiable, it has to be continuous, wherever it's differentiable. So g of x is going to be continuous. So when I take this limit as h goes to 0, g of x plus h really just goes to g of x. So this is giving me minus 1 over g of x times g of x, so g of x squared, and then times this limit here is simply g prime of x. So I can write this as just g prime of x divided by g of x squared. And if you just apply the product rule, f times 1 over g, then you'll see you'll get exactly the formula that we have in the quotient rule. Okay, so the power rule is probably everybody's favorite rule because it's so algorithmic and so straightforward to apply. But actually, I would say that the proof or the justification for why the power rule works is probably the hardest. And I'm not saying it's the hardest because there's anything deep. There's just not necessarily like a very elementary way to attack it. Okay. Now, actually, in my own personal notes, I have 4 different proofs of the power rule. So one uses mathematical induction, one uses the binomial theorem, and I always wrestle with kind of which way to present to students. And the way I think is the simplest uses something that we've actually talked about before. And that's the idea of factoring differences of powers. Okay, but in order to do that, we sort of have to manipulate our definition of the derivative just a little bit. But I think you'll follow. So here's our function f of x, and now n is a non-negative integer. Okay, so it could be 0, 1, 2, 3, 4, etc. And so by definition, what's the derivative of this function? It's just going to be the limit is h goes to 0 of x plus h to the n minus x to the n all over h. Okay, so you see the problem that we're really trying to show this for a general n. Now, if it was x squared, we could just FOIL this out and simplify and be done. Or even if it was x cubed. If it was x to the 4th, it might take a little bit longer, but we could do it. But the problem here is that this is an arbitrary n. And so what we would have to do if we wanted to continue is probably invoke the binomial theorem to expand this. Okay, but I want to kind of avoid doing that. And what I want to do is notice that I can actually rephrase this in the following way. I can let x plus h equal y. Okay, we've seen a similar idea when we talked about functions that are differentiable being continuous and taking the limits of a differentiable function. We kind of want to do this idea. Well, it's the same thing here. And so what I can do is note that as h goes to 0, y is going to be approaching x. So I can write this as the limit as y approaches x of y to the n minus x to the n over what is h? Well, h is just going to be y, and then I can subtract x, so y minus x. Okay, and why did I do this? Because we actually know how to factor this in general. So if this was a difference of squares, this would be like y minus x times y plus x. If it was a difference of cubes, it would be y minus x times y squared plus yx plus x squared. But the important thing to note is that this y to the n minus x to the n for whatever value of n will always have a factor of y minus x. And what's going to be left is something relatively nice to deal with. So what we can do is factor the numerator as follows. So we're going to have y to the n minus 1 plus y to the n minus 2 times x, and then plus etc. And then so you see the powers of y are going down 1, while the powers of x are going to be going up 1. So eventually we're going to have y times x to the n minus 2 plus x to the n minus 1. Okay? And then all of this is divided by y minus x. And that's really convenient because these will cancel. Okay? And so all we're left with is the limit is y approaches x of y to the n minus 1 plus y to the n minus 2 times x plus y to the n minus 3 times x squared plus however many terms there are between, then y times x to the n minus 2 plus x to the n minus 1. So how many terms are there here? Well, just look at the powers of x. So here in the first term, this is x to the 0. This is x to the first. This is x to the second. And then we're just going to count up. This is x to the n minus 2. And then this is x to the n minus 1. So how many terms are there? Well, if we didn't have the x to the 0 term, this would literally just be counting 1, 2, 3, 4, 5, 6, all the way up, n minus 2, n minus 1. So there's n minus 1 terms not counting the x to the 0 term, but that means that there's n terms in total. And when I let y go to x, notice that this is going to be x to the n minus 1, this is going to be x to the n minus 1, x to the n minus 1, because I'm adding, so n minus 3 plus 2 is n minus 1, n minus 2 plus 1 is n minus 1, and of course x to the n minus 1. So I really do get n terms, each of those terms being exactly x to the n minus 1 upon applying the limit laws. And so that's the idea behind justifying the power rule. And this is a little tricky, I think. I think it's it does stretch your mind in a lot of ways, but I do think it's the easiest way to see why it's true. I think if you try to use, you can use the power rule multiple times and use kind of an inductive argument, but that sort of uses an idea that's beyond the scope of this class. Just like the binomial theorem. You may be familiar with it and you can use it, but again, this is probably the most elementary in terms of the algebra required to see why the power rule is true. So we've seen and actually justified the power rule for non-negative integers. But I want to make a note that there's actually a more general statement that you should know, and it's called the general power rule. And unfortunately, we don't have the tools to justify this quite yet, but it's so useful we might as well go ahead and start establishing it. So the general power rule states that if alpha is any real number and f of x is equal to x raised to the alpha power. So here alpha is not just an integer or a positive integer or a non-negative integer. It could be square root of 2. It could be a rational number, 1/2, 3/4, etc. Then the derivative follows the exact same formula that we had for the case for a non-negative integer. It's just alpha times x to the alpha minus 1. So this is something to keep in the back of your mind because it's very useful, because a lot of times you'll have a power function that's not just x to some non-negative integer, like x to the 1/2. Square root of x, for instance, falls under this general power rule. So just so you know it's there, and when we talk about logarithmic differentiation later on in the course, we'll actually go back and justify this general power rule. Okay, so we want to just start taking some derivatives. Now, if you look at these functions, once you see the answer, and maybe you already see the answer right away, this first example is kind of a joke, but it's really not a joke because it's very important to understand the difference between constant functions and other functions. Okay. For both of these functions a and b, well, this is the square root of something, but it's the square root of 5. So this is just a number. This is a constant function. Same thing with e to the 6. Now you may be tempted to say, oh, okay, e to the x, the derivative of e to the x is e to the x, so the derivative of e to the 6 should be e to the 6. But no, e to the 6 has no variable, it's just constant. No matter what the input is, it's always just e to the 6. This is, again, a constant function. Don't get tripped up on trick questions like this. If you just have a number, no matter how crazy that number looks, and you take the derivative, you get 0. So in both cases, f prime is just 0. So that is as easy as it gets. So don't miss out. All right, so here's two polynomial functions. Now, what are polynomial functions? They're basically just taking constant functions and the identity function, multiplying them together, multiplying by scalars, and adding all those terms together. Okay, so actually for these problems, we're going to use a combination of the power rule, the sum rule, and the constant multiple rule. Okay, and at some point, you really don't need to think, okay, here's all the differentiation rules I'm thinking. You should just get to the point, or try to get to the point, where taking derivatives, especially of relatively simple functions, like polynomials, comes very naturally. So let's look at the first function. What is f prime of x? Well, f prime of x, this is a sum of two functions, f of x. So I can just take the derivative of x squared first. But that's just an application of the power rule. The power rule says the derivative of x squared, I bring down the power 2, and then I take 1 away from the power. So it's 2 times x to the 2 minus 1, which is just 1. And then plus, I can use the sum rule. The derivative of 1, well, 1 is a constant, so that's 0. So the derivative is just 2x. And now you could verify this by using the definition. This is not too different than a function you may try to take the derivative of using the definition of the derivative. But look how great it is just to use the differentiation rules. You just say, okay, you can just look at it. And if you look at enough of them, this is going to be the easiest problem. You're just going to look at this function, know what to do, know that the derivative is 2x using the differentiation rules. We can do something very similar for b. So for b, now the first term, 3x to the 4th, has a constant multiple. So we have 3, and then the derivative of x to the 4th is 4 times x to the 3rd. Okay, so I just leave the constant multiple alone. Take the derivative of x to the 4th, which I bring down the 4, take 1 away from the power. Then I have minus 2, and I need to take the derivative of x squared again, which is just 2x. We already saw that up there. And then plus 6x, so that's just 6 times the derivative of x, which is 1. So that's just 6 times 1. Okay, and then we can, of course, simplify it. This is 12x cubed minus 4x plus 6. And so that's the derivative. Easy as pie. This would be very difficult to do explicitly from the definition, but what we've done actually in this lecture is do a lot of the work for you. Okay, so actually justify this power rule. I think that's where a lot of the work is, to say that really if you have a power, this x to the fourth, I don't need to expand x plus h to the fourth every time. All you have to do is just bring down that power, take one away from the power, and we're done. Okay, so this first function, we want to take the derivative. And one of the key things when you start taking derivatives is to just make a mental note of what's going on with the function. And maybe if there's more than one function you see, how are they being combined? And so here I see the function t squared right there, and then the function e to the t, and they're being multiplied together. So this is a product of two functions. So that tells me I need to use the product rule. So what does the product rule say? Well, the product rule is pretty easy to get the hang of. All you do is just pick one of the functions. I'm just going to pick t squared. Take the derivative, so 2t, and then multiply by the other function. Then you add, okay, so I took the derivative of t squared first. Now I'm going to take the derivative of e to the t. Well, that's just e to the t. And then times the other function, t squared. So it's the derivative of the first times the second, plus the derivative of the second times the first. And that's it. And notice I really am not even going to simplify for right now. I mean, we could factor out, a factor of e to the t, but, it says just find the derivative, and this is the derivative. That's the answer. That's the derivative function. So that tells you the instantaneous rate of change of this function. It tells you the slope of the tangent line. So you're seeing how powerful these differentiation rules are. We're taking relatively complicated functions and learning a lot of information about them just by this procedure of finding the derivative function. Okay, so this function, h of r, is 1 over r to the 3 halves. So what do we want to do here? Well, for now, it looks like this is a quotient, right? So it's a quotient of the function 1 and the function r to the 3 halves. And so the quotient rule was, let me just write it out here so you can see it. So it was low times d high minus high times d low over low squared. Now, of course, high and low mean top and bottom, like that. So it looks like h prime of r should be, okay, low, that's r to the 3 halves, times d high, well, the derivative of the numerator is the derivative of 1. That's a constant, so the derivative is 0. And then minus high, so 1, times d low. Well, d low, r to the 3 halves, is really, now there's a couple of ways to think about it, but we can actually just think about it as being a power. So it's r to the 3 halves power. So what we can do is say this is, bring down the power, so 3 halves, times r to the 1 half. And now notice 1 half is 3 halves minus 1. We take 1 away from the power. And then all over r squared, the low squared. But r to the 3 halves squared is r cubed. this squared, low squared, is r cubed, because when I square that exponent, I can just multiply the exponents. 3/2 times 2 is 3. Okay, so what do we have? We have minus 3 over 2. So we have this minus 3/2. And then r to the 1/2 over r cubed, which we can write as minus 3 over 2 r to the 5/2, because I can just subtract 1/2 from 3. And that's the derivative. Okay, so this is an example of the quotient rule. Okay, so I want to find the derivative of the following functions. And both of these are examples of the quotient rule, because we see very clearly a quotient of two functions. There's a numerator and a denominator. So since the quotient rule is the trickiest, let's just practice. Low d high minus high d low over low squared. So g prime of t here, low, which is t plus 1, times d high, which is 0, minus high, 1, times d low, which is also 1. The derivative of t plus 1 is just 1, all over t plus 1 squared. But this is just 0 minus 1 over t plus 1 squared, so minus 1 over t plus 1 squared. And there's the derivative. All right, so we can do the same thing for h of r. H prime of r should be low, 1 minus r squared, d high, which is 3r squared, minus high, r cubed, and then times d low, which is minus 2r. So the derivative of the denominator is 0, and then minus derivative of r squared is 2r, all over 1 minus r squared, that whole thing squared. And so we can simplify this if we wanted to, and later it will be helpful to simplify derivatives. But for now, our goal was just to find the derivative of the function, and we're done. We have h prime of r equals something that is the derivative.